In this video we will explore the forgotten math behind an engineering subject, namely the meaning and measurement of surface roughness. We will shed some light on obscure formulae which are often written in mechanical engineering textbooks or handbooks, for which no explanation nor derivation seems to be found anywhere. For those of you who are mainly interested in pure math, don't worry, there will be plenty, ranging from trigonometry to Taylor series, after a brief introduction of the subject. Please take a look at the time tags in the video description if you want to skip to the parts you find more interesting. But I really hope you will stay with me throughout all the video, to find out what this story is all about. What is surface roughness then? Let's take for example a metal rod. Even though its surface may seem flat and smooth, when we look more closely, it will be pretty evident that, at a microscopic level, the surface is instead bumpy, spiky, simply uneven. The profile of the surface is rough. So, how do technicians and engineers evaluate the amount of roughness of the surface profile? There are a few parameters that were defined for that purpose. Maybe the simplest one is the difference in height between the highest peak and the lowest valley of the surface profile. This is the maximum roughness of the surface, and it's called Rmax or, more often, RT. But this isn't exactly a great parameter to work with. A single high peak on the surface profile may be responsible for a high RT measurement, whereas the surface might be perfectly flat and smooth elsewhere. A more useful parameter is the average roughness, and it's calculated as follows. First we, or usually, the dedicated instrument, need to determine the average line of the surface profile. Mind you, this is not the average roughness parameter already, it's just the first step in its calculation. So, how can we express this average line? We may consider the lowest valley as height 0, so that we can assign a height h to each point of the profile. And, the average of all those heights h, which we will call mu, will be the height of the average line we were searching for. The technical term for average is arithmetic mean. Be careful, this is not equal to the average between the highest peak and the lowest valley. That one is called the median value of the profile. Instead, we're interested in the arithmetic mean, which is the common average between values. Think about the average speed you record when going for a ride with your bicycle. That is not the average between the maximum and minimum speeds you reached, but the average between all the speeds you were riding at, for each instant you were pedaling. That is the arithmetic mean value. The average line of the profile is usually defined as the one that minimizes the sum of the squares of the profile deviations from the average line, for all points of the profile. The arithmetic mean happens to fulfill that exact requirement. So, how do we calculate it? Let's first consider a simpler theoretical case, in which we have a discrete surface. In this case, the whole length on which we want to evaluate the surface roughness is divided in a finite number n of intervals of equal length, each with its own height hi. The arithmetic mean of all the heights is the sum of all the heights themselves, divided by the number of different heights recorded, which is 1 for each of the n intervals. By the way, this is how dedicated instruments work, recording discrete values and carrying out the calculations accordingly. We can now go back to our real-life continuous surface. Let's draw the x and y axis and, on the x-axis, let's mark as 0 the starting point of the surface profile, and with L the ending point. So, L is the length on which we are going to evaluate the profile roughness, which, for short, is called the evaluating length. Let's now consider the profile curve as a function h of x. Now, the mean value of the function h of x is expressed by this formula here, where the integral replaces the sum of the previous discrete surface example, and represents the area under the profile curve. This area is then divided by L, the evaluating length, which replaces the finite number of discrete intervals in our previous example. The geometric interpretation of this formula is very important, as we will use it extensively throughout this video, so please look carefully. The evaluating length, L, is basically the flat base of the area under the curve. If we were talking about a rectangle, when we divide the area by the base we will get the height. So, that formula tells us that the mean value mu is simply equal to the height of a rectangle that has the same area and same base as the shape confined between the surface profile and the x-axis. That is the geometric interpretation of the mean value mu. Once we got the average line of the profile, for a specific point x0 on the evaluating length L, we can measure or calculate the deviation of the profile height from the average line, and let's call this deviation epsilon. This specific deviation epsilon depends on the specific point x0. So, in general, epsilon will be a function of x, since each different point of the profile has its own deviation from the average line. According to our definition, the function epsilon of x is equal to h of x, which is the height of the profile, minus the mean value mu. And, what about negative deviation, when the height of the profile sits below the average line? As you will see pretty soon, we are only interested in the magnitude of the deviations epsilon. Thus, let's consider the absolute value of those deviations, so that we'll be dealing with positive values only. Finally, we are ready to find the average roughness, which is called Ra, and is defined as the arithmetic mean of all the absolute values of the deviations epsilon, along all the evaluating length L. And, as we saw before, the arithmetic mean of a certain quantity is calculated as the integral of that quantity, divided by the length on which that quantity is evaluated. And, again, the integral represents the area under the surface profile curve, and we have to divide it by the evaluating length L, that is multiplying by 1 over L. Please note that all those areas count as positive, so that the integral really represents the pink area there, thanks to the absolute value inside the integral itself. If we didn't take the absolute value of the deviations but the actual deviations, which can be positive or negative, the result of the integral would be the sum of the signed areas, where the purple ones are subtracted from the pink ones. But this is not the case for the definition of the average roughness Ra. Okay then, time for a quick recap. We saw how the roughness of a surface profile can be described by the maximum roughness Rt, which is the maximum difference in height of the profile, and by the average roughness Ra, which gives us better information about the surface profile, is less affected by possible random peaks or valleys, and involves more complicated calculations. There are many other parameters which dedicated instruments would measure, but these two are the most essential ones and the ones we will be focusing on in this video. Now, what we are really interested in, is to evaluate the roughness of a specific surface, which is the one we get with a metalworking lathe, which, in modern manufacturing, is often a CNC machine, a computer numerical control machine. So many things are produced with this kind of metalworking. Here is how it works. I'm not trying to be accurate with real-world explanations, nor with terminology, but I just want to give you a quick overview. Let's take our metal rod again, which will serve as our generic piece to be machined. Let's clamp it in our metalworking lathe. The spindle is the device that clamps and makes the metal rod rotate at high speed. Let's make a sign or a scratch here on the metal rod, so that we can actually see it rotating in this simplified drawing. Here we go. Now, here is the cutting tool, which is the device that will make the machining on the metal rod. It is provided with a cutting insert, which is the part that will actually cut and remove part of the material of the metal rod. The cutting tool is not rotating, whereas it is the piece to be machined, our metal rod, which is rotating, as we saw before. Rotation at high speed is needed to achieve the peripheral linear speed necessary for the cutting insert to cut away the material of the metal rod. Typical rotating speeds go from hundreds to thousands of revolutions per minute. The cutting insert has a specific cutting radius, also called nose radius, which we will call R. The cutting radius is usually expressed in millimeters. The cutting tool is moving forward against the metal rod with a certain speed, which is expressed in terms of how much it moves forward per each revolution of the spindle. That's called the feed length per revolution, more simply the feed rate, or feed, for short. We will call it F. The feed rate is usually expressed in millimeters per revolution. So, let's see how the machining process works. As the cutting tool moves forward, part of the metal rod surface is cut away, or removed. We are left with a metal rod with a reduced diameter. Actually, in the real world the cutting tool is not positioned as shown in this example, where it is parallel to the axis of the rotating metal rod, but for our simplified explanation and for the final result, nothing will change. We want to find out how the machine surface looks like. But, before doing so, let's take a look at the metal rod surface before it is machined. During the machining process, the cutting insert, with its specific cutting radius, R, is moving forward in the feed direction. After each revolution of the metal rod, the cutting insert will remove part of the metal rod surface. The metal rod machine surface will show the footprints of the cutting insert's round tip. Here is how the machine surface looks like. Actually, those peaks are exaggerated here, since the feed rate is usually much smaller, hence the resulting surface is much smoother than that. Anyway, the footprints of the cutting insert always determine a rough surface. Also, if we look even more closely to the surface, we will see that there is an additional roughness, at a microscopic level. That occurs in the real world because, at a microscopic level, the profile of the cutting insert can't be perfectly rounded, nor a perfect material removal can be achieved with the machining process. And, if we go down at a molecular or atomic level, you see that the concept of flatness totally doesn't make sense anymore. However, in our idealization, we will only take into account the ideal profile given by the footprints of the cutting radius, discarding other possible contributions. Let's assume there is no additional roughness at a microscopic level. That would give a very small contribution to the overall roughness anyway. So, here is our machine surface. Here is the radius, R, of the cutting insert. And then here's the feed rate, F. Please take a few seconds to realize why the feed rate, according to its definition, is that particular distance, from peak to peak. R and F are the known parameters. The radius r depends on the geometric construction of the cutting inserts available on the market. So, we can consider it as a fixed parameter. The feed rate is instead a parameter which we are free to choose for each specific machining process, as it is an input value that the metalworking lathe requires. For a computer numerical control lathe, it is a parameter we have to write in the specific program of the specific machining process. For example, by looking at the drawing, you can immediately realize that, when the radius r is the same, a lower value of the feed rate f allows to get a smoother surface. Okay then, for this machine surface, how do we calculate the roughness parameters RT and RA, which we learnt before? This is the end, but just of the introduction. Now we're ready to dig deep and to approach the heart of our investigation. Don't miss part 2 of the video, where thing will really get interesting.